today we have a great pleasure to invite Tian Yong from Central University. And Tian Yong got a PhD from National Central University in 2014. And since then, and has been a postdoctor until now, still at the Central. And he's an expert on actually originally working on some of the related to general relativity as a PhD thesis, and now more recently work on some of the modified gravities and also something related to the dark matter properties. And today he will be talking about mass velocity dispersion relation in the how do you say this? What's the
HIFLUX.
HIFLUX. Basically, what's the pronunciation for it?
I'm not so sure.
Do you know? Galaxy clusters. And I think he has always been working with some people here, like with Keiichi, and also maybe Pepe? No. Do you work also with Pepe?
No.
Eno. Okay. So let's welcome Tian Yong's talk.
Thank you very much. It's my honor to be here to share our recent work on mass velocity discrepancy relation in HIFLUGCS galaxy class. My name is Yong from National Central University. Our work just recently accepted by HIFLUGCS. And here's my collaborator, FLUx, and Dr. Li Tongfei and Professor Stacy McCall from Western Reserve University, and also Professor Gao Zhongmin from NCU. This is my outline. At first, I will introduce some scaling relation in galaxy. It's about the kinematical relation and the dynamical relation, known as the baryonic two-division relation and the radial observation relation. And later on, I will explain our recent work on the similar relation in galaxy cluster. There's a clash, IR, and the MVDR. So I will briefly introduce the famous two-division relation. Two-division relation is about, for each spiral galaxy, there is a plate pair, and for each galaxy, we can measure the total luminosity. The two-division relation is a relation about the luminosity and the rotation velocity. People find it we can fit a straight line to this galaxy, and it gives us the luminosity is proportional to the velocity to the power of 4. And if we consider the mass is proportional to the luminosity, it will be a little bit difficult to understand that in the standard Newtonian dynamics. Moreover, beside the relation between the luminosity and the rotation velocity, Stacy finds there's a tight relation between the baryonic mass and the flat velocity. So in order to get the baryonic mass, we consider the gas-rich galaxy. On the left-hand side, this panel shows the for the red line here, its meaning is when the stellar mass equal to the gas mass. So for the there are 43 spiral disk galaxy here. This galaxy has the gas mass is more than the stellar mass. And the gas mass can be measured from the 21 centimeter. So we can have the precise gas mass. So with this mass and adding with the stellar mass, combining other spiral galaxy sample, Stacy gets a tight relation from this so-called baryonic 2D feature relation. The mass range is about 5 to 6 order. And in this relation, if we fit with this one, then the intercept will give us acceleration scale, constant acceleration scale, but this scale is very small. This capital G stands for gravitational constant. So that's about the kinematical relation. So recently, Stacy and his team discovered a tight acceleration relation from spiral galaxy. By using the Spitzer telescope, there are 153 spiral galaxies, and among them, because they can plot the internal region, there are about 2,700 data points. The vertical, there are two independent measurements for two axes. For vertical axis, the so-called observational acceleration or the total acceleration was defined by the Newton dynamics. The velocity was measured from 21 centimeters. And for the horizontal axis, we have the baryonic acceleration defined by the Newton gravitation, by the Newton gravity. And the baryonic mass here composes two components: the stellar mass from the near-infrared band and the gas mass from 21 centimeters. So the dotted line here represents when these two accelerations are equal. But here, the data point shows there's a discrepancy. So the observational acceleration is larger than baryonic acceleration. If we interpret the observational acceleration as the total mass, then which means there is a missing mass in this system. This relation is tight. The inset presents a histogram of the residual. So the residual presents as a Gaussian distribution, and the half Gaussian width is about 0.11 dx. So this is a tight relation.
Excuse me. You say the gas mass come from 21 centimeter?
Yes.
How about molecular gas? Molecular gas.
Molecular gas. I don't think they come for that. Let's spiral galaxies are close by.
Right. There should be lots of molecular gas. Neutral hydrogen should be just part of the gas.
Thank you. And this data point can be fitted by a relation. They were using this function, the function of the baryonic acceleration. And in this relation, it's introduced an accelerational constant. This acceleration scale was in the low acceleration. It is very small, and the arrow for this acceleration is also small. If we plot the residual in terms of the baryonic acceleration, there is no obvious correlation. So, what do we learn from this relation? It's a tight relation. It was first mentioned by Henry Desmond. He writes the full issue for this relation. The first one is, what is the physical origin of the acceleration scale, the small acceleration? And the second is, what is the physical origin of the low acceleration slope? Because for the low acceleration, it can be asymptotic by a straight line. And this straight line will give us the slope. It's about 0.5. And the third one is the intrinsic tightness of this simulation. It's smaller than 0.11 dx. And the last one is the lack of correlation between the residual and the other galaxy properties.
Excuse me.
Yes.
Another question. So, dotted line is the error dot.
Oh, yes. That line is the error bar.
Coming from like a scatter among the sample.
Yes. And for each red beam, this will represent the mean error for they beam the data set. So that's how they get the red one.
But this error is basically the scatter among the sample.
Among sample, yes.
So is that error on each sample?
Error for each
So
sample.
you just take each measurement as a.
Yes.
So, but is there any error on each measurement?
Yes. They did the error analysis for each data, because there will be the data mainly come from the mass acceleration. When the near infrared is about 3.6 micrometer, and the mass ratio ranging from 0.42 to 0.6, and they take the mean value as 0.5. So they have further analyzed by Dr. Li Pengfei, and he found the main error just comes from mass ratio for the stellar mass.
I see. And that scatter becomes so small. I mean,
Yeah.
this is 10 to minus 11, so this answer is extremely small.
Yes, but if they using the NCU method to get the accurate mass ratio, and when they did that, the scatter nearly disappeared. They published a serious paper in 2018. And
So how many galaxies are included here?
153. Any more questions? And here was analyzed by the Federico Lai. He analyzed the residual in terms of different galactic properties, such as the baryonic mass, effective radius, and the surface density, and the fraction between the stellar mass and the gas mass. So there's no obvious correlation between these quantities. Okay, that's for spiral galaxy. But we have another different type of galaxy. For spiral galaxy, it's a rotationally supported system. And for equal galaxy, that is a pressure supported system. But how about the equal galaxy? Likely they find some data in outer 3D, and there are some rotating equal galaxy. And there are also some X-ray equal galaxy. They do find the data point is consistent with their spiral data. We also did some related work. Professor Gao Zhongming and I studied the gravitational lensing by using 53 unsigned ring. That is the relativity effect of the equal galaxy. And then we do find this, the data shows it's consistent with the spiral galaxy. Moreover, that's for the ASIAA, radial acceleration relation. And if we consider the difference between the observational acceleration and baryonic acceleration, this difference can be defined as a halo acceleration. And by combining with our sample and the stated sample, and together we get that's the black data point. We find there's a maximum halo acceleration for this one. And if people fitted the data by different function, then in halo acceleration relation, it can be this different function to be distinguished by the data point. So here is a short summary of this. So we have the dynamics and the kinematics. In the solar system, it's well known that we can apply the Newtonian dynamics, Newtonian laws, Newton's law for dynamics. And for the kinematics, we have Kepler's law. They can be derived to each other. But for the spiral galaxy, for the galaxy, now we have the radial acceleration relation as an empirical dynamical relation, and then there is a corresponding kinematics, that is the 2D feature and the factor extent relation. Oh, I think. Oh, I missed one page here. Sorry. So I have to talk about the relation between the 2D feature relation and the radial acceleration relation. Since there is a low acceleration limit for the ASIAA, the radial acceleration relation, we will have this relation. And by considering the Newtonian dynamics and the Newton gravity, then we put this quantity into this low acceleration limit. It can recover the 2D feature relation. In history, people did that in the opposite way. People guess this relation just from the 2D feature relation. Okay, so next I will talk about the scaling relation in galaxy cluster, our recent work. Here is one example of the galaxy cluster. Galaxy cluster is the largest gravitationally bounded system. And we know there is due to the strong gravitation, there is an X-ray gas, and it's dominant for the baryonic mass. And we also have the Mbar galaxy and the central galaxy as a 5-inch cluster galaxy. But their mass are not accounted for the total gravity. So usually the mass fraction between them for galaxy is just about 1%, and for the X-ray gas is around 10%, and about 9%, and for dark matter is about 19%. Dark matter is dominant in this system. And in order to study the radial acceleration relation, we need the observational mass and the baryonic mass. So for observational mass, we consider the strong and weak lensing analysis from page image 2016. And for baryonic mass, we need study the X-ray gas and the stellar mass, and as well as the BCG. So here I introduce the Clash cluster. Clash stands for Cluster Lensing and Supernova Survey with Hubble. It is an outstanding project which composes 25 high temperature and massive cluster in the sky. Clash cluster can measure the interior region of the galaxy cluster. So we will have the data to do the radii visualization. Here's my collaborator, the Clash team, Kenji from HIAA and Megan from Michigan State. And also Yong was previously in HIAA. And in the Central University, it's Professor Gao Zhongmin and I. So here is our result. For the left-hand side, this is the result if we consider the gas mass only. Then the data are more scattered if we add in the stellar mass here. But by considering, although the gas mass is dominant inside the galaxy cluster, but we still need to study this is the gas observation. And but for the right-hand side, we correct the baryonic observation by considering the empirical relation between the stellar mass and the gas mass. So by adding this stellar mass, the relation seems become tighter.
You mean the stellar mass is not actually measured?
It's not actually measured.
It's inferred from gas mass.
Yes. Yong's paper is from South Pole telescope, but the mean mass is close to the Clash data. So when he gives us this empirical relation, then we account for data at different radius. The radius here is at 100 kilopasecond, and we have data at 200, 400, and 600 kilopasecond. For different radius, then there is a different ratio between the stellar mass and gas mass. So this will introduce some scatter into this relation, since this is not directly from measurement, but from empirical relation. By combining, and we know there's in the center, there's BCG, brightest cluster galaxy. So if we consider the BCG into our relation, then together, it seems they can be fed by a straight line. The red diamond here represents for 20 BCG. This is our result. By fitting with the NCU method, we get the slope is 0.15, which is very close to 0.5, the low observation limit of the area. And the dashed line here represents the stasis result from spiral galaxy. So there is clearly an offset between this relation. This instead represents the histogram of the residual. It's still a Gaussian. And we get the half Gaussian, which is about 0.13 dx. So it's very close to IR's result. So here is the comparison between our, we call that the Clash IR, or BCG and the cluster scale. And this is the IR in galaxy scale. They are similar, but there's offset, which means the total observation or the total mass is larger. It's much larger than what we get in galaxy. And it raises a question: since these two relations are very tight, so if we know some baryonic observation, then we can get a total observation, and vice versa. But in order to understand that in in a standard dark matter model, in a dark matter model. So we do some tests for it. We consider the MW profile for dark matter, for MW profile for dark matter mass model. And we also consider the parameterized gas model for to fit our data. So the solid black line here represents the MW profile. The parameter was taken by the mean of our sample. We have 20 galaxy clusters, and they are the mass range are similar. So when we consider the mean of this sample, then our profile since can fit the data point, and as well as the gas profile. So here is the result. The color rectangle represent our semi-empirical model at different radius. The same color represent the same radius. Oh. Okay. Sorry for the interruption. So the same color represent at the same radius. And then the error bar was analyzed from the Monte Carlo simulation, since we have different scatter for the parameter. And our result is consistent to the data. Here is the residual analysis in HIFLUCS. The red diamond represents for BCG, and the gray dark point, gray circle represent for our cluster data. There seems a correlation in the radius, but for other quantities such as baryonic mass, surface density, and the redshift, the correlation is not obvious. So how about the implication of this result? This HIFLUCS differs the relation between the total acceleration and the baryonic acceleration, which is very similar to the low acceleration limit of the ASIAA. And if we consider the Newtonian dynamics into this relation, it will give us the mass velocity dispersion relation. The mass, baryonic mass, will proportional to the velocity dispersion up to the power of 4. So that's my motivation to try to study this relation. So here is an update for the fall issue. In the previous study for the fall issue, we have the acceleration scale and the low acceleration loop, intrinsic scatter, and no correlation between the residual and other galaxy property. And our result, for the first time, we discover a new relation in the clash galaxy cluster. So we get a new acceleration scale, which is about 6 times larger than the acceleration constant in galaxy. And the acceleration slope is close, is about 0.5, which is very similar to the ASIAA. And our intrinsic scatter was analyzed by the NCU. This the logarithm of the intrinsic scatter is still small, but we do have a correlation between the residual and the radius. So here is the summary for the dynamics and the kinetics. So right now, for the cluster scale, then we have a clash ASIAA. So how about the implication for the MVDR? So in the literature, some people try to study the relation between the temperature and the gas mass. And Sanders in 1994, he defined, if we interpret this temperature as the velocity dispersion, then people can get the mass is proportional to the velocity dispersion up to the fold. But the data quantity here is not good. So there's a lot of scattering in this relation. So I try to measure the velocity dispersion from Mbar galaxy. So we analyze the cluster in a HIFLUx sample. There are 64 galaxy clusters. HIFLUx sample, the highest X-ray flux galaxy cluster sample. The criterion of the subsample, we consider the cluster center of say between the BCG position and the X-ray flux weighted cluster center is smaller than 60 kpc. So we should reduce our sample from 46 to 51. And moreover, we require the Mbar galaxy, we collect them from the literature. It has to be more than 30. So there are only 29 clusters have the required condition. So here is one example. This is the albeit 85. The two-dimensional distribution for the Mbar galaxy. And each, the box and the cross represent the relative velocity to the center of the BCG. Here, the dotted circle represents for the radius of R500. And this is the two-dimensional analysis of the line of sight relative velocity. We can, by considering the arrow bar of the velocity, then we can get the velocity dispersion. So it seems from this sample, then we have the flat velocity dispersion in the tail. Here is the 3 examples of our sample. And this for the smaller galaxy cluster we have in 4max. And it seems for this cluster, we all have the flat tail. So by considering the last data point as the flat velocity dispersion, then we get the mass velocity discrepancy relation here. The vertical axis here is the baryonic mass, which composed of the X-ray mass and the stellar mass. The stellar mass is still from the correction by the empirical relation. And the horizontal here is the velocity dispersion, line of sight velocity dispersion. So here is the inset is the histogram of the residual. Our half Gaussian width is still small. It's about 0.12. And then this is the residual analysis. We analyze the residual in terms of the temperature and the radius, characteristic radius of the cluster, and the baryonic surface density and the redshift. It's still no obvious correlation between this cluster quantity. And in order to understand this in dark matter model, we we test a very simple simple model here. The enclosed total mass within the radius in lambda CDN can be given by this relation. The mass with the enclosed the critical density and multiplied by its value, R. And for the dynamic for this is the dynamical mass, the dark matter mass, and for the dark matter mass, we can relate it to by gravitational potential the gravitational potential traced by the velocity dispersion. Then we will have this relation. So for these two relations, if we eliminate the radius, then we can relate the dark matter mass as the velocity dispersion. So the power is to the 3. And we find there's the red region here is the relation if we apply for this this relation here is for the dark matter mass, but we need to consider the baryon fraction here to convert the dark matter mass for the baryon mass, and for the cosmic baryon fraction, then we assume this one is constant, and for the observation, the value we take 0.13. So if we consider this as a constant, then we will have the baryon mass proportional to the velocity dispersion to 3. So here is our result. And there are some constants here: gravitational constant, Hubble constant, the baryon fraction, and the latest proportional constant is Jeans factor. It can be analyzed from the Jeans equation, and it's typical from the square of the Jeans factor is from 3 to 5. So it will give us the red region here. So for the small galaxy cluster, and since the relation there will be a discrepancy between the relation between the dark matter prediction and the data point here. This is another implication from the clash area. In clash area, because we will have the total observation, we'll have the relation between the baryonical observation and the observation constant. So if we divide it by the baryon observation, it will give us the cosmic baryon fraction. And the cosmic baryon fraction will have relation with the baryon acceleration. And this so we test this relation by using the HIFLUX cluster, and it seems the data points are very close to this relation. The upper panel here is if we consider the baryonic mass, then the relation is not, the relation is loose. It seems we have to introduce the radius into this scatter. This is the summary of the work given by considering dynamics, kinematics, and the lensing. So, this is for kinematics when people analyze for the 2D visual, vector relation, and the mass velocity discrepancy relation. And this is analyzed for the dynamics of the IR or glacial IR. And this is the lensing. So For the spiral galaxy and the elliptical galaxy, the results are consistent to each other. They are all following the radial acceleration relation, the ASIAA. But for the galaxy cluster, we discovered that the relation is similar, but have a different acceleration scale. But our result for the mass velocity dispersion relation is consistent to our classic ASIAA. Here is the remark. In galaxy, the ASIAA will give us this relation for the low acceleration limit. And the baryonic 2D field relation will give us this one. They have the identical acceleration scale, independently measured from different measurements. The values are consistent to each other. But in galaxy cluster, for the first time, we discovered a new relation. The classic ASIAA gives a similar relation, but with a new acceleration scale. And the MVDR in our sample gave us this relation. Okay, I will stop here and take questions. Thank you.
Thank you very much. Any question for Tian Yong?
What do you think about the picture totally relating now? There seems to be more tighter than ever than other current theory or otherwise. I mean, this is a relation that really looks strange. It's too good. It is too good relationship. So I'm afraid I won't be convinced until somebody can have a real clever idea. That's really required.
When I did this analysis before, I have no idea what result I will get. We do check our data many times for each detail and each possibility. But for two different samples, we get consistent result. I would like to get some more sample to understand why we get the result here. Because when people study the relation between the mass, if we study this relation by considering the mass here, they are not as tight as the acceleration. So I really don't know why. Why is that? Why we have to use the acceleration, and we can get the tight relation, no matter if galaxy or cluster.
There are some people arguing that this tight correlation is a consequence of Mond. So those Mond people are using this as a supporting evidence.
Yes, but I have to be fair that our result in cluster will have both problems for calculator and Mond. Because Mond, so far, the original idea cannot extend this the offset, but the slope was exactly the same as Mond prediction in galaxy. So I really don't. I have no idea.
Yeah, as Pablo said, so the more people are so excited because gravity is supposed to scale free, but yeah, analyzing galaxy scales, some people found this specific acceleration scale. But by analyzing galaxy clusters, we found a different acceleration scale. So actually, there's no such universal relation. Yeah. So I think this is very important finding from our papers. Yeah.
Probably those Mond people need to add another parameter.
Yeah, basically in galaxy clusters, the baryon fraction is dark matter fraction is so high, so it doesn't work. Right? No, it doesn't work. And actually, there are many authors involved in this acceleration relation in the context of reminiscent. Recently, team by the Ravishes, yeah. So they are analyzing the mock galaxies created in the the lambda CDM universe and try to understand this relation from astrophysics. Yeah.
Any other questions? Anyone?
I think I missed something. So for in this plot, the data point for the clash, I just wonder, you need the velocity of the information of velocity, right? I just
For clash data, the total acceleration was analyzed from a strong and weak lensing. So it's relativistic effect.
So basically, total mass divided by r squared. That's acceleration.
okay, I see. Okay, so the y-axis is measured from the lensing, which include all the mass.
Yes.
basically. And then the x-axis is from the baryon.
Yes.
But I'm curious then, if you want to compare to the dashed line, which is measured from the gas kinematics, right? Or I mean, for the spiral galaxy.
For spiral galaxy.
Yes, right.
Yeah. Yes.
And let's see. Okay, so I guess I kind of misunderstood the relationship. So I thought that originally for the spiral galaxy, let's see. Okay, so the velocity from the gas also include. So another question related is that I wonder for those spiral galaxy, what's the radius they measure the rotation curve? What's the radius when they measure the velocity, right? Because for galaxy, as far as I know, for massive galaxy, if it's close to the galaxy, stellar mass dominate the mass budget.
Yes.
Right? And then you need to move to a larger scale so that dark matter will gradually become dominating component of the
Yes.
mass. Right?
Yes.
So I just wonder when they measure the
Okay. So the space telescope can plot the internal region of the spiral galaxy. So whatever they get, they just put for their. Okay, so for in their spark data, there are 2,700 data points. So for each spiral galaxy, there are about 10 more data points, and they put all the data they have into this diagram. So they measure no matter the interior region or the outer part or the flat one. They all follow this relation.
okay, I see.
And
Okay.
for the case of crash, so our measurement is from like 1% of the period radius up to 50% of period radius. Because we are probing from BCG scale to the 1 megaparsec. Yeah. So the dynamic range is totally different for the crash. But we don't really resolve the BCG internal region. Only one data point.
And how did you identify the central point of the cluster?
For the crash sample, there's actually a selection effect for the 16 out of 20. So they are chosen to be, have a small offset between BCG and the X-ray center. So there's a completely well-defined center. And 4 others are margin clusters. So for them, I think we defined the center to be like X-ray peak. Yeah. Like simulated the potential. Yeah.
DC.
So if you go back to the cluster RAR, the offset, I could view it as the offset on x-axis, meaning that at the same y-axis, the cluster has a lower baryon gravitational force, acceleration.
What do you mean for?
So I can move, if I want to move the cluster relation to the spiral galaxy relation, I can just increase the x-axis by a factor of 2.
A factor of 2. The offset is about 16 times larger. So
no, I
if
mean
you
in x-axis.
in x-axis,
Yeah, so
Oh,
I don't doubt
yeah, yes.
I don't doubt the total variant because it's from weak and strong lensing.
Yeah,
I think that's solid. The question I want to ask is how good can we confine or constrain baryon mass? I mean, that's
It's very tight because we measure X-ray.
I see.
That means 90% of the baryon in clusters.
Right, ionized gas. And we don't expect any systematics from X-ray measurement.
Very small. Basically, we have Chandra measurements and XM measurements.
Yeah.
For the gas mass, it's very accurate or consistent.
And that's coupled with sinusoidal wave factor.
Not for this.
Not really. I thought if you want to get the accurate mass, you need both NCU effects and X-ray.
For the gas mass, basically we can tightly measure it from the X-ray brightness.
Okay.
Temperature is more difficult.
Right.
We need SE and X-ray to really deproject in 3D.
I see.
Yeah.
So actually, crust is one of the high mass cluster sample.
Yes.
Instead, HIFLUX sample contains not only clusters but also massive electrical galaxies and groups. So then, even crush, you can find deviation from the expectation of the galaxy scale. But for HIFLUX samples, it's very good sample to extrapolate to from galaxy scale to cluster scale.
Yes, for small, that's why I find the HIFLUX simple because the mass range is larger, and for these two, one of them is FLUx, and then the other one is NGC 64 26 galaxy group. Yeah. So maybe they compose of the doped gas. So that's why the baryon mass is small. But for the clash simple, it will be here. But so far, we don't have the complete galaxy membership. So we cannot add to that. But I'm curious about the small galaxy cluster, since the data point here is not enough for this.
You mean that the higher side, upper side of this data point is consistent with
I didn't know, but I mean the mass range for clash will be around here. Will be even massive than the HIFLUX sample.
Okay. Any other questions or comments?
Well, one more. So sorry, I still quite not understand the spiral galaxy. The curve. Could you go back to the spiral galaxy curve again? So for the high massive end, it becomes consistent with the baryon, right?
And that's not mass, that's acceleration.
Do you mean?
Okay, so the
These two axes are all acceleration, but the definition is from Newton dynamics. In Newton dynamics, we have two definitions for the acceleration. One is for the Newtonian dynamics. The other one is from the Newton gravitation law. Now there's a discrepancy between these two relations.
So could you go back to I think it's previous slides for the information used. One is from the velocity, right? Another is from the mass, right? So,
Yes, this was defined by the Newton dynamics.
okay.
And then this was defined by the Newton gravitation law. We equal them because of the weak equivalence principle.
But the G bar here, the mass to estimate is from only baryon, right?
Only from baryon.
On the y-axis, I thought that the velocity will depend on
The potential.
total mass, right?
The total mass, yes. This can be interpreted as a gravitational potential. And the gravitational potential can be interpreted as the total mass. So in terms of mass, we will have missing mass from this relation.
It's a bit tricky, yeah. G ops is really physical quantity, but G bar is like a hypothetical quantity. If the gravity is only given by the baryons, we could define such quantity.
Yeah, so I'm just curious, at high G bar value, the two become consistent.
So it means there's almost no dark matter in the very central region of the galaxy.
Yeah, usually they are in the center.
Yeah, so that's my understanding, that in the center of galaxy. So that's why I'm asking, is because I wonder whether or not this train is just due to the measurement of velocity as a function of radius or something like that. Because the consistency at massive M means that in the center of the galaxy is only the mass is dominated by the.
Yeah, it's basically baryon fraction, but this we are being in the acceleration space. If we consider like a correlation in the radial space, radial range as a function of the heliocentric radius, we don't find such a tight correlation.
In the again, could you say again the last sentence?
For example, if we compare like the baryon mass and the total mass as a function of radius,
Okay.
then we don't find such a tight correlation. This tight correlation is only in this space. Yeah.
Okay, I see.
That's why we are considering this.
Okay.
Yeah.
Thank you.
Okay, SK.
Just curious, I mean, on this plot, so how was the projection effect taken into account? It's not in the world, right? But the black should be a three-dimensional velocity, right?
Like.
But what was observed is the projecting.
Oh yeah, yes,
So
it's
how is
projected.
that
So
accounted
yeah,
here?
so they have to consider intention angle.
Incline.
Incline.
And also in the elliptic gas.
Oh, for elliptical gas, we only measure the projective line of sight velocity.
Now the issue is that the correlation is too tight, right? So any of the effect you consider will just make the correlation not so tight. So
Yeah,
that's
yes,
the
yes.
So there must be some projection, right?
Yeah, it will just make the correlation less tight, right? So now the issue is that the
And
correlation
then how can you
is too
measure
tight.
so tight a relationship? I mean, there
That's
is projection.
That's exactly the problem. So that's the missing physics that people are.
Well,
trying to-
these are corrected for projection, the inclination angle.
Yeah.
Yeah, so these are corrected for inclination angle, right?
Yes.
But
From the measurement.
But for elliptic galaxy, then how do you?
Or if you assume virialized body,
And,
then
isotopic.
velocity dispersion, then it's fine.
Okay, good timing. So let's thanks Tian Yong again.